Hello, and thanks for joining us for yet another episode of Space Nuts. My name is Andrew Dunkley. Coming up in episode 307, we're going to Mars. A couple of things on Mars. The copter, Ingenuity, has done some more amazing things and set a couple of records. And we've found out why Mars is perpetually dusty. I suspect it's dust, but we'll be talking about that. They've also discovered through Hubble why Uranus and Neptune are different colours. Do I need to elaborate? We will. We'll also be answering a couple of questions about neutron stars and escaping the Milky Way in a spaceship, I assume. Apparently difficult. We'll try and figure that one out on this episode of Space Nuts. Stick around.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as he always does, is astronomer at large, Professor Fred Watson. Hello, Fred.
Hello, Andrew. Yes, still at large. They haven't called me yet.
No, they haven't, but they might.
Yeah. Who knows?
Just keep running, Fred. Although I find at my age, running is not ideal. Don't enjoy it at all.
Well, that's all right, because at my age, running is impossible. So.
Fair enough.
Yeah.
Okay, let's get on to our first topic, and we've got a couple of stories from Mars. The first being that the Ingenuity Mars helicopter is in the news again. This thing is just doing some amazing stuff, and it keeps making the news for that reason, and this is another one of those stories.
Isn't it a great story, Andrew? Who would have thought a helicopter on Mars to start with, one that works, one that does a sensational job, but that keeps on breaking its own records, which is fantastic. I think when we spoke about Ingenuity at first, it was expected to complete 5 flights, of which the first 3 were going to be testing out all the kit, and the other 2 were whatever they could do. The moment Ingenuity is preparing for its 29th flight, so it's doing a marvellous job. And obviously the team built it, put their heart and soul into it, and did all the right things, because it's been a work of art in terms of what it has achieved. And the reason why I mentioned record-breaking is that back in April, on the 18th of April, it actually had a record-breaking flight because it was the furthest and fastest flight to date. And I've got the figures here in both sorts of units. It's 704 metres, 0.7 of a kilometre. That's a significant distance, which is 2,310 feet. And it achieved a speed of 12 miles per hour, which is 5.5 metres per second. So certainly, you can probably run a bit faster than that. Maybe not, but
don't think so.
But it is. It's a fast pace, and you'd have trouble keeping up with it. I think anybody. So fabulous stuff, and still doing sterling work. That record-breaking flight, you can actually find footage of it on the web. I'm looking, as we often do, Andrew, the phys.org website, and there is footage of the flight, which has actually been compressed. It's speeded up 5 times. So
I'm just watching it now.
Yeah, isn't it great? So you've got a sort of footage of the surface of Mars gliding by beneath you from an altitude of 10 meters or 33 feet. A lovely quote from Teddy Sanetos, I think is his name. He's at JPL, Jet Propulsion Laboratory. For our record-breaking flight, Ingenuity's downward-looking navigation camera provided us with a breathtaking sense of what you would feel like gliding 33 feet above the surface of Mars at 12 miles per hour. That's exactly what you get. And it is. It's great. It's lovely.
Yes, it is. And I suppose while it's still operational, they'll keep operationaling it. They'll keep going because you sent it up there for a reason. Okay, it's done everything they wanted it to do. But now I suppose it's an opportunity to really test this thing to the limit of its capability, and just keep pressing on to see what else they can learn, and it opens the door to what may be able to be done in future missions to Mars.
Exactly, yeah. And I suspect, the mission controllers here, they probably got a little bit of dichotomy because they probably want to do just what you've said: test the thing to the limit, see how far you can push it, how fast it can go, how far it can go before something goes wrong and it's broken. But the problem is with that this little helicopter has turned out to be really useful in terms of finding the way for the Perseverance rover, checking what's beyond the next ridge, looking for rocks that have got interesting features to them, and essentially just scouting out the landscape around Perseverance, which is, I'm sure, what mission controllers hoped it would do when it was being developed. Because remember, all it's got on board is a camera, the navigation camera, and I think there might be two, but the navigation camera is certainly the main one, the downward pointing one, because it uses that to find its way autonomously. Got its own brain inside. Nobody's controlling it because you can't do that from the Earth with the long time interval between signals going up and coming back. So it thinks for itself. I think the mission controllers say, I want you to go there, and off it goes and works out all the details itself. So remarkable, and such an achievement there. I think I'm correcting myself there. I think I said there might be two cameras. I don't think there are. I think there's only the navigation camera on board.
Okay, yeah. I wonder how far it could go away from Perseverance before, it was irretrievable. Is it tethered to Perseverance by radio or anything, or is it totally autonomous?
I think it is. Maybe I think most of the hardware is actually sort of computing hardware is on board the Ingenuity, the helicopter, but it certainly would talk to Perseverance, yes, without doubt. I think they've already smashed the records that they expected to achieve. If I remember rightly, it's when it was built, I might be remembering the wrong number here, but 150 meters or 160 meters sticks in my mind as being its maximum range. And yet this record-breaking flight, 5 times that or thereabouts, 704 meters. So it's already pushing the limits. I guess what the worst thing might happen is if its batteries failed in flight, although I think the sensors on board would tell the autonomous system, look, your batteries are running out, you better get down to the ground, because if the batteries failed in flight, that could be catastrophic. If it landed on a surface that had a hidden rock or something and tipped over, I think that would be the end of the story as well. Yeah. You want that solar panel, which is absolutely essential for keeping the battery topped up. That's got to be facing upwards. And if it's pointing downwards, it's end of story, I think.
Yeah. Well, we've heard stories like that about other rovers.
Yes, indeed.
That have lost power because they just couldn't get exposure to solar energy. So,
Philae.
It's always a risk. But
exactly what happened with Philae on the Rosetta mission.
Yep. But incredible so far, and can't wait to hear more about what they're up to with Ingenuity. Let's stay on Mars, Fred, because it's a dusty place. It's perpetually dusty, and they think they now know why. Now, it might seem strange for us to actually be trying to come up with an explanation as to why Mars is dusty, because it's a red planet and it's got weather. So you would think, well, duh. Yes. It's going to be dusty, but this is a permanent haze.
It is, that's right. And it's why the sky's slightly pink on Mars, because that's the dust atmosphere-borne haze. Yeah, you're familiar with some of the dust storms that we can get on Earth, those gigantic clouds of dust that come in western New South Wales from time to time. And they get that on Mars as well. They get these enormous dust storms, sometimes blanket the entire planet. The last time that happened, I think, was 2018, which is, Curiosity, the rover that was on Mars, got a fairly solid coating of dust on that. But even when there's no global dust storms, it's still a hazy planet. And so, essentially, what is it keeps the dust particles aloft? That's the big question. And the studies that have been done, and this is research that's coming out of a multinational team of researchers from the USA, Spain, France, Finland, looking, of course, at data from Perseverance and other rovers on the surface of Mars. They have demonstrated that those huge dust storms that we've just been talking about are not often enough to explain why the planet's always hazy. And so what they've done is they've looked at the Perseverance rover and what it can tell them. And in particular, Perseverance has a set of sensors which are called the Mars Environment Dynamics Analyzer. Mars Environment Dynamics Analyzer. I'm having trouble reading stuff today, Andrew. Otherwise known as MEDA or MEDA, MEDA. And it's a weather station, basically. Air pressure, temperature, wind speed. There's probably not much point trying to measure humidity because it's usually about 1 or something like that. But anyway, it also has equipment that lets you analyze the sunlight to see how much light is scattered through dust. So that tells you how much dust there is in the atmosphere. And it's in fact, I think it's connected with the dynamics analyzer that the Mars microphone is installed, because we've talked about that too. Anyway, the results from that are really interesting. And one is, and it's probably not that much of a surprise, but the dust devils, these little whirlwinds that you're familiar with in Western New South Wales. I used to see
familiar.
them.
Yeah, we get some really big ones here.
Yeah, I used to see them when I lived in Coonabarabran. They are apparently more frequent than was expected. And the reason why that doesn't surprise me that much is that I've more than probably a decade and a half now, I've been showing, if I talk about Mars, I tend to show a little video clip that came from, it was one of the early rovers, Spirit, I think. Yes, the Spirit rover, not Opportunity. Spirit and Opportunity were the pair of rovers back in the early 2000s. Spirit sat itself on top of a mountain range called, actually it's one mountain called Husband Hill. It's in the Challenger range. All the peaks in that range are named after people who were lost in the Challenger disaster. Husband Hill is one of them, and they looked at the landscape beyond, and there's all these dust devils charging across the landscape. So just one little bit of footage from one spot on Mars, and what do you get? Dust devils. Apparently, that is common to Mars, certainly at least in the equatorial regions where most of these landers have found themselves, including Perseverance. And the suggestion from this research is that at least one dust devil is generated in the vicinity of the rover every day. And that's sort of more common than we get here on Earth.
Yeah.
So the dust devils on Mars, of course, are quite different from the ones on Earth. I think the biggest one I ever saw, and it was actually driving back from Coonamble in Western New South Wales towards Coonabarabran, and it would have been, my guess is 500 metres high. That's pretty tall for an earthly dust devil.
We were driving home from Queensland once in a very dry time of the year, and I think the region was in drought, and we were driving across the Moree Plains, which is north of us, a few hours north of us. And we saw two massive dust devils, and they would have easily been 200 or 300 metres high, just big red tornado-like structures.
Amazing, that's right.
Gosh, quite extraordinary to watch. Yeah. So we had one. We actually had, since we've lived in this place, I've had two dust devils come over the top of me while I've been in the backyard.
Oh, really?
And the updraft is quite incredible. And cleaned all the yard, picked up all the leaves, took it away. Didn't have to. It was quite amazing.
Somewhere else.
I stayed still. But
it's a good thing you did.
They just pick up so much stuff. They're amazing.
That's the beauty, of course, with these dust devils. With the earlier rovers, Spirit and Opportunity, they cleaned off the solar panels. The dust devils going by actually swept the solar panels clear of dust. Now, Curiosity and Perseverance have both got thermoelectric nuclear generators, so they don't have solar panels. But really interesting. Yeah, that.
Now, I assume the dust devils on Mars, you said they're different, so I'm guessing they wouldn't be nearly as big, or are they bigger?
They're 8 kilometres.
Whoa!
Yeah.
Whoa!
Yeah, they're huge. I think I'm remembering that number correctly. They are very, very tall. And it's partly that the dust is very fine, but also the gravity's lower. Of course, against that is the atmospheric pressure being low, so you wouldn't think the winds would whip up as much, but they do. And the other thing about them, because of the low humidity, Andrew, here's one that would be a surprise on Earth. You get little flashes of lightning in the base of them. as the dust particles rub against one another, they generate static electricity. So you get these little flashes of lightning, and I've seen footage of these being captured. So different to dust devils from what we get, but they have got a role in cleaning up the spacecraft there, which is very nice. However, there is another aspect, though, to why Mars is dusty, and that is that there's a phenomenon which essentially generates wind patterns, what they call daytime upslope winds.
Okay.
So it's something, again, it's not as common as the dust devils, but essentially just a phenomenon of atmospheric heating that gives you these rising winds. They blow up the slopes. And once again, good old phys.org's got a lovely piece of footage of this actually happening, a gust lifting event, actually top of a hill there, showing quite clearly a huge patch of dust being carried by the wind, as it rises up the slope. And that is now thought to be another major contributor to why Mars has this constant atmospheric haze.
Yeah, quite amazing. We have similar things happen on Earth, particularly in desert regions.
Yes.
But I was quite struck by coming into land in Dubai and looking out the window, and just this red haze in the sky all the time, and it's there all the time.
Yeah.
So it's the same kind of situation, probably a different effect. But yeah, I can imagine that's what Mars would be like in terms of the everyday, is seeing this constant redness in the sky, and that's what it's like around the United Arab Emirates, and I'm sure many other desert countries. It's quite incredible. But yeah, I noticed that going in there. I think it would be the same in parts of the US, some of those more desert-like areas around Las Vegas and similar. But yeah, well, we know what it is now. It's wind. And I meant to mention, and dust devils, I meant to mention there's a great scene in the movie The Martian. I know I've talked about The Martian many times, and it's a great movie. I love it. But there's a great scene where he's driving the rover along this plains area on Mars, and they've put a beautiful piece of music into the scene where he's driving through these dancing dust devils. It's really worth seeing. Yeah. It's only a very short scene, like 5 or 10 seconds.
Yeah.
But it impacted on me greatly because it was just so beautifully done. I know it was all CGI, et cetera, but it was It was a brilliant scene. I thoroughly enjoyed it, and I'd watch that scene again just to watch the whole movie again because it's so well done, and it just sort of gives you that impact of isolation and desolation all at once. I don't know. Yeah, I think that's a great piece of cinematography. Yeah, so now we know. This is Space Nuts. Oh, by the way, if you want to read that article, phys.org is the website. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, let's move on from Mars to a couple of other planets in our solar system. And they're planets we do talk about occasionally, but they don't seem to get as much attention as the likes of Saturn and Jupiter. We're talking about Uranus and Neptune. Now, I didn't even think about this as an issue, but obviously somebody has been going, I wonder why they are different colours. And they've been analysing this through the Hubble Space Telescope, and they think they've figured it out.
Exactly. And in some ways, it sort of follows on a little bit from the last story because it's all about haze. So what we've got is these 2 ice giants, Uranus and Neptune. Uranus the nearer to the sun and slightly larger than Neptune. But generally, you can classify them together. Their masses are not too different, and their sizes are not too different either. And their atmospheric composition is very similar. And yet they have a different appearance. And I'm going to, this is beautifully put in the Hubble Space Telescope press release that I'm looking at, which is entitled Hubble Helps Explain Why Uranus and Neptune Are Different Colours. What they say is at visible wavelengths, Neptune is a rich, deep azure hue, whereas Uranus is a distinctly pale shade of cyan. And that's It's almost greenish, actually, is
Yes,
Uranus.
I've seen photos that
Yeah.
actually suggested it was closer to green.
Yeah. I mean, often in photos, it's the color balance of what you're looking at that determines what color they look like. But yes, so this is the formal analysis: a rich, deep azure for Neptune, and a distinctly pale shade of cyan for Uranus. And
Before you go on to explain why,
yes,
I'm wondering why we would assume they should be the same color.
and it's because of the similarities. So when you
Which you
look
already
at
suggested, yeah.
and in particular, I think the atmospheric composition, because they're sort of rich in methane and hydrogen and all the normal sort of elements, but they have strong similarities. And I think the bottom line here, Andrew, is that because of the similarities in the composition of the atmosphere, albeit Neptune's is a bit colder because it's further away from the sun, but because of that, you might expect that they would look identical,
Right.
and they don't. And so, what is being done is, first of all, lots and lots of observations of Neptune and Uranus from the Hubble Space Telescope, as well as actually ground-based telescopes, including Gemini North, that's in Hawaii. Not very far from it is NASA's own infrared telescope facility, the IRTF, which is one of the oldest telescopes on Mauna Kea in Hawaii. And they've used observations from that as well. And what they've done is, and I should say that these researchers are led by a professor of planetary physics at Oxford University, but with other collaborators. His name is Patrick Irwin. What they've done is they've analysed all the observations, but they've also built models of what these atmospheres look like. And I think essentially there's a bit of simplification going on here, but what they've got is a 3-layer model of the atmospheres of both of the planets. And it turns out that the 3 layers are differentiated by the amount of aerosols that there are in. So particles, essentially, within those layers at different heights. And it turns out that what the layer that affects the color is the middle layer. And it's, in fact, they call it the aerosol 2 layer because it's the middle of the 3. And it's apparently thicker on Uranus than it is on Neptune. But what they believe is happening is that you essentially have methane ice, which condenses onto the haze particles, whatever they are, the dust of some form, and that sort of pulls those haze particles deeper into the atmosphere. I love the language here. In a shower of methane snow. So you've got this snow falling through Neptune's atmosphere, so through Uranus's atmosphere. Beg your pardon, that's on both of them. So you've got that effect on both of them. But it turns out that Neptune has a much more turbulent atmosphere than Uranus. And we know that Neptune has some of the highest winds in the solar system.
That surprises me, that it's more turbulent on Neptune.
Yeah, it does a bit, because you'd think Uranus being close to the sun would have more heat going into the...
That's not what I was thinking.
I know. I'm trying to clean up your act, Andrew. Lift your game, that's doing. Dear. Anyway, notwithstanding all that, what they say, the turbulent atmosphere of Neptune, for whatever reason that might be, they suggest that atmosphere is better, sort of essentially churning up, as they put it, these methane particles to produce the snow. And it keeps the haze out of the way. That's the bottom line. It has this snow going down, gets the haze out of this important layer. And that is why we see the Neptune we see what you might call its true color. It's blue, and Uranus would look like Neptune, except that it's got more of this haze, which kind of whitens it slightly. That's basically the bottom line of the research. One of the other collaborators in this work, who's at University of California, Berkeley, Mike Wong, says, "We hope that developing this model would help us understand clouds and hazes in the ice giant atmospheres. Explaining the difference in colour between Uranus and Neptune was an unexpected bonus." It's quite nice that they've done that. But they now see that this whitening effect of the larger amounts of haze in that middle layer of Uranus's atmosphere is why it looks paler. It's why it doesn't look as deep a blue as Neptune does. Get rid of the haze and it would look just the same.
Yeah. Does that suggest they had identical origins, or perhaps came from the same place?
Yeah, it's possible. That's right. I mean, they are suspiciously close together when they're adjacent in the solar system. They're a long way apart, as planets are at that distance. But they are, they may have had a common origin. They formed in the same bit of the protoplanetary disk that surrounded the sun. So
that's amazing.
Yeah, it's nice stuff. They also actually, incidentally, they've investigated some of the other aspects, because both of those gas giant planets, or the ice giants, Uranus and Neptune, they have dark spots on them, which are interpreted as being atmospheric storms. And in fact, some of the Voyager pictures show some of those dark spots. And this modelling that they've produced actually explains what gives them the darker appearance, and also why they're more easily seen on Uranus than Neptune. Really interesting research, and they're to be congratulated, I think, on sort of answering so many questions about these two mysterious planets.
Yes, indeed. And again, if you do want to read that article or the media information from Hubble, it's on the esahubble.org website, esahubble.org. And I did state at the beginning of this particular segment, Fred, that we tend not to spend as much time talking about these two planets. We focus more on the rocky planets and the gas giants. But I've been doing a little bit of research while you've been talking, and apparently the reason we don't pay as much attention is, particularly in the case of Uranus, is that there's a significant risk in staring at Uranus too long, because you could get arrested.
Dear, irascible is the word. Irascible. Yes, you had to do it. Yeah, that's true. Yeah,
had to do it. Oh dear. You are listening to Space Nuts.
Yeah,
sorry.
I was going to say I'm as guilty. It wasn't my fault that I wrote a book called Why is Uranus Upside Down? It was the publishers who chose that, not me. It's the best-selling book I've ever written.
And you're sticking to it.
Yeah.
Yes. He's going to have to update it so that he can change the colour of the spot. That's on
exactly
Uranus
right.
too,
Yes.
I think it's brown. This is Space Nuts with Andrew Dunkley and Fred Watson.
Yes.
Space Nuts.
Okay, Fred, let's tackle some questions. We've got a few to go through today. Two of them focus on neutron stars. We did talk about neutron stars a couple of times recently, including the mountains on neutron stars, which are, 3 millimetres high?
Yes, something like that. That's right.
Anyway, that seems to have provoked people. Well, they've come up with some questions. This one from Christian. Hi, I love the podcast, and I've got a question I'd like to ask. If you could stop a neutron star spinning and get up close, would its surface be like a mirror, or does its density and weird physics make it a translucent crystal? Really enjoying listening to you both. Take it easy. Christian Tadman. Thanks, Christian. Well, it's a big ask, stopping a neutron star and then getting close to it. Let's just assume you can for a moment.
Yes. I think the answer is that it wouldn't look like a crystal, because we know that neutron stars have structure. In fact, they contain not just neutrons, but protons as well, which is where the magnetic fields and things come from. I understand it. Their surface is structured like proton. The emphasis on protons. The neutrons are concentrated in the center, in the core. So it's already got structure, which probably would rule out it being transparent and something you could see through, like a crystal ball. But of course, it's also got a hugely hot surface temperature, typically around 600,000 degrees Kelvin. So that means that the radiation that would be leaving it is firmly in the ultraviolet. Bless you, Andrew.
Thank you.
And it's a very weird and wonderful place. Now, the reason why we can see neutron stars is because of the fact they beam out the radiation, the radio radiation, along their axes, their magnetic axes. In other words, their north and south magnetic poles are where it beams out from. And the fact that they're rotating, sometimes up to 43,000 revolutions per minute, which is astonishing for a star, that rapid rotation is why we see these lighthouse pulses of light that we call pulsars. So they come from neutron stars. I think you have a follow-up neutron star question. Is that right?
Yes, we've got another question. But stopping a neutron star, if anyone could ever do that, that would they would have all the power in the universe, I imagine.
Yeah, they probably would.
Yeah, the second question is an audio question. This one comes from Simon.
Hi, guys. Love the show. My name's Simon. I'm from the UK, but living in New York. My question is specifically about neutron stars, which absolutely fascinate me, even perhaps more than black holes. My question is, assuming that you would survive the radiation and the crushing gravity, could you actually walk on the surface of a neutron star? It would seem that they are so dense that you could actually walk on it. My next question is, them being so dense, how do they actually emit any radiation? I don't quite understand how that might work. I'm dying to know what Fred can tell me there. Anyway, great show, love it, love every episode. It's the best podcast there is going. Keep up the great work, guys.
That's nice. Thank you so much, Simon. So a double header. Can you walk on the neutron star? Well, easy to climb the mountains, that's for sure.
Yeah, and I think that's a clue to the answer to that question, Andrew, that we've talked about mountains on neutron stars, and you're right, they're a couple of millimeters tall, which suggests that they would have a solid surface. And I think that's really what Simon's asking. Do they have a solid surface? Yes, of course, the gravitational pull would crush you to, nothing really. And the radiation would be a problem, but it does seem that they do have a solid surface. So the other part of Simon's question about why, a neutron star can irradiation at all because of that gravitational field is a good one. The answer is that they do, because of course we see the evidence from the beams of radiation that are channeled out along their magnetic poles. And the magnetic fields themselves contribute to that because they're huge, up to 1 quadrillion times stronger than the Earth's magnetic field, which apparently is 10 to the power 15. So there's a clue there too, because black holes do the same thing. Their magnetic fields are so intense that they can squirt jets of material out from their poles. And we talked recently about the one that's tilted over with respect to its accretion disk. So that intense gravity is not necessarily a barrier to stuff leaving it if there are other strong forces as well. But the bottom line with a neutron star is it's not a black hole. So it doesn't have an event horizon, which is that point beyond which you can't see anything because light itself cannot escape for a black hole. So neutron stars still allow radiation to escape from the surface, and that's why we can see them. It's why we can observe them directly, unlike black holes, which we can only observe by virtue of the effect they're having on their surroundings, the radio radiation that comes from the accretion disk with all the material jostling and charging up to very high energies.
Very good. Thank you, Simon. And thank you, Christian, for your questions about neutron stars. And we've got a question from Duncan. This is sort of a science fiction question.
Hello, Duncan here from Weymouth in the UK. Just a quick question. Many sci-fi series, such as Star Trek, Star Wars, etc., depict escaping from the Milky Way in a spaceship as being very hazardous. I just wondered if indeed that is the case. If you were out there in a spaceship, would you be able to escape the Milky Way easy, or is there some huge barrier or reason why you couldn't? Some, I don't know, shear as you head out of the Milky Way. I don't know, really. Just a quick thought. I mean, I couldn't think of any particular reason why it would be different. I imagine it would just get thinner and thinner with stars, and eventually there'd be nothing around you. But I don't know. Just wondered what your opinion on it was. Thanks.
Thank you, Duncan. Love the accent, by the way. I must confess, I don't recall ever hearing it portrayed in any science fiction that I've watched or read that it's difficult to get out of the galaxy or anything to that effect. But obviously, Duncan's come across it. Would it be hard to sort of launch yourself beyond the galaxy and get out into interstellar space?
If you had enough time, you could do it. It'd
Just
take
assume we've got time.
a few billion years, because the speeds we move at compared with the size of the galaxy it will take a long time. I think though Duncan's right in that, as if you imagine the Milky Way itself, its structure. So you've got this disk of stars and gas and dust. You've got a halo, a much more rarefied sphere, mostly of stars, not much gas in there, globular clusters as well, which gets thinner as the further away you get. So if you were leaving sort of perpendicular to the disk, you'd first of all have to cope with all the disk stars, and that's fairly highly populated in the vicinity of the sun. But then you'd start going through the halo, which is much more rarefied, not much gas and dust to speak of. And beyond that, you're in intergalactic space. Yeah. So I think there isn't what you might call a physical barrier, but the main barrier is the gravitational one. So the galaxy sits in a gravitational well. Its gravitational pull is more than what you would expect from what you can see, because we know there's dark matter there that's tending to hold it together. And when you add all the matter together, the baryonic or normal matter plus the dark matter, that means that you've got this gravitational force or gravitational pull to overcome. And it's not ridiculously high. It means that what it means is that our galaxy has an escape velocity, just like a planet does or a star.
Yeah.
On the surface of the Earth, to get off the Earth altogether, you have to be traveling at more than 11 kilometers per second. That's the escape velocity from the Earth. And we know that the galaxy has an escape velocity. And in fact, some of the work I did a decade or so ago, along with many collaborators, actually allowed us to measure the escape velocity of the galaxy. The International Rave Survey that I was project manager for, RAVE being the radial velocity experiment, we measured the velocities and other characteristics of 500,000 stars in our galaxy, fairly locally in the galaxy. But by looking at their motion, you can actually calculate what the escape velocity would be in our neck of the woods, our part of the galaxy. And I'm trying to remember, because it's a decade or so ago that we did this, but I think it's around about 240 kilometers per second. So considerably more than the Earth, of course, to leave the galaxy. So you'd need a lot more thrust than you do to get it off the Earth. But it's not inconceivable that you could achieve a velocity of that sort of magnitude, a couple of hundred kilometers per second.
Yeah.
So, that would be, I think, the main barrier to leaving our Milky Way galaxy.
Velocity,
that's right.
Velocity and gravity. Yeah, okay. Duncan, thank you. Really good question. Love those kinds of what-if questions. And you prepared for a question without notice, Fred?
I am.
Yeah, we got one through our YouTube feed a little while ago, and it basically comes from Ollie. He said, I guess I was wondering, as I take astro photos, and of course I can adjust the colour as I please, I wonder how people like Fred, who analyse these photos from a scientific standpoint, if there are specific colour calibration rules they need to adhere to, etc., or if it's not an issue. He said, sorry, not well explained. But look, I understood it. So, Fred, what do you reckon?
It's a great question. And actually, look, the person who is the absolute master, the maestro on this is David Malin, my colleague and good friend. We had dinner together a couple of nights ago. David pioneered the technique of putting true color into celestial images back in the 70s and 80s. And the calibration processes that he went through were interminable, calibrated them to death. And it's all about, not just getting white balance. It's just about the gamma curves and all these fancy terms that you use in imagery to get them all matched, so that what you're seeing is an absolutely true representation of what you would see if your eyes were millions of times more sensitive. And it's that because other astronomers knew that these images have been so well calibrated, that led them to be able to make scientific discoveries from them, just because they knew that the colors represented the real effect. So it's a great question. And if David was sitting here now, he'd be talking for the next half hour about how he did it.
So the answer to your question, Ollie, is yes, but we don't know what those specifics are in terms of colour calibration, but I suppose it's circumstantial. It's what you're photographing.
To some extent, it depends on your technique. Look, it's pretty easy to find. I mean, in a sense, the question's well made because a lot of that calibration is now taken care of in the software that you can get, which essentially, it's artificial David Malin is some of the software you're talking about because it does those calibrations for you.
All right. Thanks, Ollie, and thanks for listening live. Good to hear from you.
Yeah.
And don't forget, if you've got questions or comments or ideas, hypotheticals that you want to send through to us, you can do that via our website, spacenutspodcast.com. Click on the AMA link to send us a text question or an audio question, or you can click on the tab on the right-hand side of the homepage to send us an audio question as well. And while you're there, check out how to become a patron if you want to support us financially, because there are lots of people that do that these days, and we really appreciate it. And there are various ways: Patreon, Supercast, or you can just click on the buy us a cup of coffee button and make a one-off small donation, or you can leave a review on your favourite podcast distributor. The more reviews, the more people that get the attention of us, or we get the attention of them, and the bigger our Space Nuts community grows. So, you can leave reviews through whatever platform you listen on. Fred, that wraps it up for another episode. Thank you so much.
They come around so quickly.
They do.
It's a great pleasure, Andrew. Always great to talk, and looking forward to the next time.
We'll see you next week. Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks for listening. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.